Um, okay, Perry, you're up next. We'll have to hear about the research and development of the post and plate system writ large.
All right. Well, as mentioned, my name is Perry Forsythe. I'm a professor at the University of Technology, Sydney, or these days I'm an emeritus professor because I've sort of semi-retired from that and do some consultancy work for the industry and still have an honorary role at the university. My interest is in research, particularly applied research, and that's what this is, an applied R&D project. It's about post and plate construction. And I guess this picture on the left is a kind of a semi-comical mock-up of it. You can see that we have these columns. We use special connectors. If you follow my cursor, we didn't use ones exactly like this. We actually use ones by Rotoblast, a spider connector that I'll talk about in more detail later. So this just gives you a snapshot of what post and plate is. No beams, obviously. This is an idea that Andrew Dunn, who'll speak after me, and I became interested in. I guess we thought that the engineering design was quite innovative and interesting, but whilst it met aspirational requirements, it didn't necessarily meet process requirements on site. So we wanted to change what we thought was a relatively aspirational idea to one that was more practically achievable. And as part of that, we used digital twinning, or what's also known as 4D building information modelling, to improve the process on site and to incorporate those process requirements in the end product. So it wasn't just an architectural product and an engineering design. We were aiming to build in things around the process that made it efficient and cost effective and things of that nature. So as you can see here, why post and plate? I've just alluded to some things. Speed is one. Simplicity of a reduced number of components and relatively easy to put together is another reason. And I guess one of the big underlying issues is here that we're trying to be competitive with concrete construction, and particularly what's known here in Australia as flat plate concrete construction. The flat plate meaning it's a fairly thick slab, but it means there's no beams and you just have columns and perhaps a capital of some sort involved depending on the span. And so we're trying to compete with that. And I guess one of the reasons is this issue of no beams. You can see on my drawing on the right, I've drawn in the beams in yellow that you often see in post and beam timber construction or mass timber construction. And often those beam depths mean that one floor level has to be left out of the allowable building envelope height in order to meet structure requirements. So on the right, you've only got 4 floors because of the beam depth. On the left, you can see with post and plate, we have managed to get in an extra floor level. And of course, this is governed a little bit by the development approval process of local government. They'll give you, or there'll be issues around what's the achievable envelope height. And so if you're a property developer, you want to get the maximum lettable yield, square meterage of floor area. There's also less complexity for mechanical, electrical and plumbing services. Unlike deep post and beam scenarios where the beams have to have deep or large penetrations for ducting and wiring and, for example, cold water supply, or where cold water supply might even dip under the beam and then come back up, which is unsightly. This situation deals with that quite nicely. Less site labour. We've essentially, apart from the fact that it's a prefabricated approach, it means that we've cut out a whole level of construction in removing all the beams, so less layers involved. This means a smaller kit of parts, and I guess you could say some from stock. So if we go back to that previous slide here, you could imagine that these columns could pretty much come from stock, and the sort of spider connector by Rotoblast is also from stock. It's flat packable, so in terms of delivery from potentially long distances away, you get quite a lot of economy in the delivery. It's not like large 3D volumetric pods and things like that, where you're essentially transporting quite a bit of fresh air. That's not an issue here. It's a pretty repeatable design platform because it's a grid layout. It has its economic sweet spots in that grid layout, but in terms of a production platform, you can fairly readily stretch it within that, or to a degree, within that economic sweet spot. It suits economies of scale in that it can handle a 3D model from CAD that goes into a computer-aided manufacturing with a CNC approach fairly readily. Brock Commons was perhaps one of the first using this system. It's a Canadian project. It's a bit of a benchmark, mainly for process. It's not a particularly exciting architectural building, but it was quite engaging as the way things could or should be done in terms of on-site process. You can see here, and if you follow my cursor for a minute, you can see that the columns, they're relatively closely spaced. We're only talking 3 to 4 meters, or in fact, probably not even 4 meters. But you can see these posts a bit like legs, and then on your opposite side, and they're supporting a table of sorts. So very easy, and you can see the spacer bars help hold the top of the column grid in place, which meant the columns were fairly rigidly located for landing these tabletop pieces. It meant that there was relatively little propping of the columns that you can see here. This was a 18-story student housing, and that's why there's such a close column spacing. It's not that different compared to, say, a jail cell. They did 2 floors plus per week. That's very fast. If you were doing this in concrete on a 930 square metre floor plate, you'd be looking at a much longer than that. For this scale of building, you might be looking at more like 10 to 14 days or something around there. There was only a 9-man install crew, 6 hours for floor panels to be placed. And remember, you're close to 1,000 square metres here. As little as 3 hours for the columns. You can pick that up that they used a semi-manual or a manual method, which as you get to larger scale buildings is not really achievable because the columns become too heavy, but it worked a treat in here where they just plopped the columns into the metal plate on the floor. They used 4D process modelling, which is essentially what we did. We thought that was a good idea. It seemed to work very well. Everyone on that project really liked the 4D modelling to assist their understanding of how the process would work in detail. So we wanted to realise this potential in an extended application of post and plate for construction in Australia. We were looking at new connector systems. We used a number of them, but because of time constraints today, I'll just focus on the Rotoblast Spider connector. There's some new mass timber concepts. One of those was the band beam system that Katie just spoke about. We wanted to apply it to different building types because even though Brock Commons worked well for student housing, it's a very small column grid. And so quite restricted. We wanted to look at more like suburban office development, institutional buildings, and even to some extent, multi-story residential, which can be used here or is maybe used for flat pack concrete here, because it allows the developer to not commit to wall layouts until late in the project after their, or it means it's flexible right up until late in the project, which they can adapt to suit changing market conditions. As we go to longer spans of 6 and 7 metres and perhaps even longer, the Brock Commons scenario is tested because we need more temporary support. And I'll talk about that a little bit later. The Australian conditions that we designed our process for looked at safety, compliance regulations and different supply chain conditions. Our team for it was myself, obviously, Andrew Dunn, who'll speak after me, Paul Winter, who helped with the actual expertise in converting what we wanted into a 4D or digital twinning model, XLAM and Rotoblast. As I said before, we wanted to focus on process and having that incorporated in the engineering design to make sure that this was fast, efficient, reliable, and above all, cost effective. One thing I think we need to remember is that the construction contractor makes up by far, far, far the lion's share of the price. And if they are seeing it as being an awkward process, they'll add on extra cost. And so we're trying to make this a very doable process. And what I mean by that is you're probably all familiar with floor cycles. So this ground floor first floor cycle, first, second, third, fourth, and so on. You want that to be very reliable and very fast for timber to have a competitive advantage over the in-situ concrete alternative. Within that, we have a number of sub-cycles. If you look at that in terms of concrete, you'd have form, reo, and pour, and probably some post-tensioning as well. But we're looking at trying to minimise and simplify these sub-cycles. And so this, say, for example, 2-day floor cycle is going to break down into 4 sub-cycles. We'll talk about that a little bit later. And they need to have, in production terms, flow, balance, buffering, just in time, and limited queuing. And what that means is the process, these 4 sub-cycle processes have flow in that as one finishes, it can pass on like a fast baton change in a sprint relay race. We don't have someone saying, oh, I can't come till tomorrow, or that bloke's not around for the next week. This has to be a continuous process. We need balance insofar as whatever this first sub-cycle does is producing whatever it does at a rate that is ready for the next sub-cycle to take it on. We want a little bit of buffering so that this sub-cycle, if things go occasionally wrong, not systematically wrong, but occasionally wrong, we can deal with that, or they can deal with it as a crew. But we don't want large queuing happening where this first sub-cycle is producing many times more than this second sub-cycle can handle. So we're trying to balance our crew sizes to make sure everyone's occupied, no one's hanging around doing nothing, and that it's a smooth process. And that, to some extent, incorporates this just-in-time approach. The method that we use for undertaking the project, I won't dwell on it too much because we're short for time. We made a 30 by 20 model building floor plate and projected that across, I think it was 5 floors for memory. Maybe Andrew can pick up on that one. We looked at 3 different construction systems where we tested and refined them. We did some field research and technical inquiry to identify obvious issues. One in particular was around how we temporarily supported things. Then we had an industry workshop with our tier 1 and tier 2 contractors and various members of the supply chain and specialist mass timber fabricators. We then asked Paul to create, or Andrew and I did a lot of work on this, a lot of debate between us, created Gantt charts of timing, crew sizes, things like that, put it together in a draft digital model, ran a second workshop for refinement, and then moved on to a completed digital model, which I think Andrew can give you the details on how to find. Here's the 3 versions. Here's the centre support infill system. You can see that it's just got a minimal number of columns down the centre line of the support, the main panels. We have to place these, and then we can drop in an infill panel in the middle in between them. So I'll talk about this a little bit more, but you can imagine that having a table like this supported by only 3 legs is far less stable than the sort of rock common scenario we looked at, where there was 6 legs on every table on both edges. So that became a temporary construction or on-site problem. Then we have to get this first one in place, second one in place, and then to drop the 3rd centre infill panel. In fact, we found it better to put all of these tables in place and then do the infill panels as a latter process. This is the one we're going to focus on. This uses the spider connector that we'll talk about more. This is a band beam system that we looked at with cross panels. I think Katie probably talked about something similar. I guess one thing here is you need a lot of screws to create composite action, like many screws, which we found to be on the critical path, or getting it off the critical path was important. The edge support system, pretty similar to Brock Commons, but using different connector systems. So as I said, I focused on this one, or our team focused on this 6.8 by 6.8 metre grid. This used the spider connector, which you can see on the right. I think the thing I wanted to point out here is that This cylinder on the left-hand side is typically going to be prefabricated onto the top of columns board out to site, and it'll punch through our CLT floor plates. But then you need to place the spider's arms. By the way, it's obviously an insect. It's only 6 legs, not 8. But they need to be placed on top, and then they fall into this locking ring. Whereas this piece here is sitting on the underside of the next column to go up. And we found that this created certain complexities on site. It would probably be better for these to have studs, like I'm thinking like an engine block type stud, where they come down through the plate, and this particular ring can be more easily fixed to it on site. We found that from our point of view in Australia, we'd prefer to do fixings from underneath over on the deck here, if you follow my cursor, fixing up underneath than having someone on a live deck. And so this tended to dictate the process that we adopted for this particular approach. It was different for the other 2 systems. And obviously, as I've said before, there's a lack of stability during fabrication. You might have a 12 by 2 metre long or 3 metre wide panel here, only supported by perhaps 1 or 2 legs. How's that going to sit there? Unless you use sky hooks, it's not going to work. So we had to think a lot about our temporary support and how to minimise that, because it's not a value-adding cost in the overall process. It's something that you have to have, but you want to minimise it. I'm going to play you a video now, but before I do, this ended up being about a 1.5 to 2 day floor cycle. We had a 12-man crew, and I'll break that down. We had a tower crane that did what you might call the heavy lifting, and a mini crane that was used for some fabrication bays, which I'll talk about later. Features the spider connection. And if you look during the video, you'll see 4 sub-cycles in our overall floor cycle. One was fabricating bays outside the footprint or the floor plate. And we refer to those as T-tables because they've got legs down the middle or columns with the spider connector on top. Then we lifted those large assemblies into place on site. Then we did that for all of the T-tables. Then we put our infill panels in, and then finally jointing and screwing. I'll just click the video and hopefully we're in business here. So you can see the fabrication bays set up on the side of the building. The orange part is edge protection for safety. You can see temporary push-pull props stopping the tables from falling over. You can see the connectors going in. They take a lot of time, and they can be on our critical path. So looking at the number of connectors is actually quite a very important thing if you're looking at time and process. So this is what happens inside making the T-tables in the fabrication bays. You can see the spider connectors going together. The spider acts like an umbrella of sorts that holds up the panel and reduces or helps assist in having a reduced span or deals, sorry, with the overall span. It makes longer spans more achievable. Andrew will talk more about connectors, but these CHS connectors and these sort of bow tie shaped things help pull the panels together and help deal with tolerance variance between the different panels. The couplers help try and transfer load. They have to be connected on the underneath and on top. So for us, it meant we'd put a team in early underneath because they're working in a safe area with edge protection, whereas we had to wait a bit longer for the top team to get on because we need our edge protection in place. We need to put edge protection around every single panel, as you can see, every T-table, so they could start putting in the spider connectors without having to wait. But once we got to a certain point, when the infill panels are placed, which will happen in a second, we were able to start removing the edge protection around each T-table. So you'll see that happen now. And the reason we want to do that is so that we can start preparing for that to be in stacks that we can then eventually crane up to the next level for the next floor cycle. Okay, so I think we'll leave that there, as it's just going to keep repeating. It gives you a feel for the spider connection and the 4 different subcycles. So as I've listed on the left there, we have this fabrication bays for the T-tables. This has an underlying assumption that there's room on the site for that. We could reorganize this to have a single fabrication bay. The fabrication bays were mainly there to help remove safety issues of putting the spider connector in place in situ, or our lack of the difficulties in creating edge protection. I think you'll see in a moment that the 2 fabrication bays aim to help make sure this spider crane, and indeed the tower crane that you see on the left here, busy. So once this guy finishes making his T-table, the tower crane will then spend time with a typical crane cycle, bringing it up and dropping it off. And in the meantime, this second fabrication bay has already started its process of making the next T-table. And then in the meantime, or once this crane has finished dropping fabrication bay once, it then picks up from fabrication bay 2. The crane cycle tends to rule your maximum speed. Here you see the sort of Gantt chart. I know this is complicated, so I won't dwell on it, but this breaks down our subcycle 1. So, for example, the blue ones here are the first fabrication bay. They overlap very neatly in this nice, consistent line. The green ones are the second fabrication bay. And you can see that our crane, which is crane cycle, which is in orange, the moment this guy's finished, the crane can pick it up. The moment the crane is finished, that dropping the blue one in, the green one's ready, and it picks it up, and there's no wasted time in the crane cycle throughout the process. Then we move to dropping in the infill panels in black. And again, that's on the same angle of trajectory, which shows a pretty good cycle. Where we take up a lot of time is these ones down the bottom. These are essentially our CHS connectors. This one is where we started on the underside of the panels, and we managed to do that without affecting our critical path. But from this point onwards, these things are taking up time and a reasonable amount. So if we're looking at speed, we really want to try to look at connector systems that reduce that. And the ones we used were available on the market, but I think there's potential to improve. So coming to a sort of conclusion and findings, pretty fast 1.5 to 2 day and reliable floor cycle. Our actual bar chart suggest about 11 hours was the minimum. The spider dictated the overall process strategy. Tower crane cycle rules the process, and that's why we use 2 fabrication bays. We tested, I didn't mention it before, but we tested using adhesives instead of mechanical connectors between the panels, which is really interesting technology. But I think for practicality, the things that affect it are the curing time. So, for example, if you have to wait 2 days, which was the sort of typical time where you can get around 80% strength, that's just added onto your floor cycle because you can't start your next one. And then the inspection test plans may also take increased length because you may need to do some level of lab testing. That's unclear at the moment. And if you do, that's more or less a separate subcontractor in the process. They have to wait for their results, which may all add to the floor cycle. As mentioned, aim for balanced crew sizes, repetition and synchronization between crews, start fixing as soon as possible. I think the digital twinning, actually, we found it to be quite effective in seeing problems with things and showing people. So it was actually quite useful in seeing, clarifying and deciding. Areas for future development. I think, well, one which we're aiming to look at is in a project forthcoming, hopefully, is managing stormwater during construction and to a lesser extent, or to some extent, wind, because it affects crane. But stormwater can reduce unwanted variables. Reduce fixing and jointing. Screwing robot is a definite idea, and craneless column installation, possibly using something like a glorified forklift. Okay, that's me. Thank you for listening, and I'll hand it back to you, Carla.
Thanks so much, Perry. All right, well, following that great presentation, we'll flow on to Andrew, who's going to talk about some of the connection considerations in post and plate systems. So off to you, Andrew.